Welcome to week 6. This is the first lecture of week 6. We'll continue with logic coverage criteria the whole of this week. Last week we introduced logic coverage criteria. I introduced you to the basics of logic. So all the coverage criteria, the active clause, inactive clause coverage criteria, elementary ones like predicate clause coverage, and then I showed you what was their subsumption relation. So this slide is a recap from last week where we saw all these coverage criteria, to begin with predicate coverage, clause coverage. Then we saw 3 categories in active clause coverage, 2 categories in inactive clause coverage. Then we saw this, for the sake of completeness, all combinations coverage, which is not going to be useful practically at all. What we will see today is take source code, see how these coverage criteria that we saw can be used to test for source code. So in today's lecture, I'll show you one example of testing using logic coverage criteria for source code. In the next lecture, I'll show you another example of testing using logic coverage criteria for source code. I decided to do 2 examples of source code, unlike graphs, because logic coverage criteria is quite predominant and popularly used. So it needs some amount of practice to be able to understand how to put the coverage criteria that we learned to practical use. So we'll do 2 examples of source code, this lecture and next lecture. After that, I'll tell you how to look at logic coverage criteria for things like design constraints, exactly like we saw for graph coverage criteria. We will look at preconditions, examples, and see how logic coverage criteria applies to them. Finally, we will take specifications as modeled as finite state machines with guards and apply logic coverage criteria to guards on them to see how it works. So that's the plan for this week. So today we begin with source code. When I consider source code, where do logical predicates come from? They come from every kind of decision statement in the source code which leads to branching in the source code. For example, they could come from if then else statement, it's labeled by a predicate. Every switch case statement is labeled by a predicate. Statements like while do while, do until, repeat until, all of them are labeled by predicates. For statements have predicates, right? So programs are studded with decision statements, and every decision statement has a predicate in it. So when I have a predicate corresponding to a decision statement, I can apply all the logic coverage criteria that we have learned to be able to test the program. Typically, most programs will have less than 4 clauses. In fact, we look at this, the number of clauses in a program and how it matters and how to apply logical coverage criteria in detail in the 3rd lecture. But typically, it's considered a good practice, or empirical studies in software engineering have shown that most programs have 4 clauses. But typically, many programs have predicate where the whole predicate itself is just 1 clause. It may or may not have and ors or other Boolean combinations, in which case all the various coverage criteria that we learned here, all of them basically boil down to only predicate coverage, right? Which means clause coverage, combinatorial coverage, active clause coverage, inactive clause coverage, everything is the same as predicate coverage because the whole predicate is just 1 clause. Now, to be able to do logical predicate coverage, where do I find predicates? As I told you here, you find them all in decision statements. The same old problem comes again, the problem of RIPR criteria, or reachability and controllability, right? So when I have a predicate that is deep down in my program that, let's say, labels an if statement, it could be that the variables involved in the predicate are all internal variables. There could be no inputs, there could be no outputs. But how do we give test cases? We give test cases in terms of inputs, and then we say what is the expected output. But let's say a predicate has no inputs, it has only internal variables, then you have to be able to make sure that a test case in terms of inputs can be written in such a way that the predicate can be reached, right? You're guaranteed to reach the statement corresponding to the predicate. That is the condition of reachability. We have to be able to get to that statement, meaning we have to be able to give input values that make the program reach the statement by executing all the statements that come prior to that. The next is controllability, or what is called infection and propagation. In controllability, we have to be able to again give input values in test cases that in some sense indirectly assign values to the variables that are present in the predicate. Let's say there is a particular predicate inside a program that uses all internal variables, and I want to test that predicate for predicate coverage. That is, make it true once, make it false once. But please remember, this predicate has all internal variables. So to do predicate coverage, I should be able to reach this predicate, and using input values, I should be able to give values to the internal variables such that the predicate is made true once and false once. That is the problem of infection or propagation put together and called as controllability. So what are internal variables? They are variables in the predicates that don't occur as inputs to the program. So sometimes, to be able to assign values to the internal variables, I need extra predicates where I can add, saying that these are the conditions that have to be satisfied to achieve reachability and controllability. And it's the same as adding the conditions as clauses to the original predicate that needs to be tested. Because one is to test the predicate, I have to be able to reach the predicate and control the predicate. So I add these as extra conditions. So we'll see all this through the example of thermostat in today's lecture, and then we'll see one more example in the next lecture. What is reachability? What is controllability? What do we mean by appending extra predicates to the original predicate that correspond to reachability and controllability? We'll see it through using examples. So as I told you, logic coverage criteria is probably one of the most important testing criteria, very powerful, used across board in all kinds of software, so it's important to get it correct, right? So I'll do source code for logic coverage criteria and illustrate the problems of reachability and controllability through two examples. The first example we'll be doing is a program for a thermostat. What is a thermostat? Thermostat is a device that controls the heating of a particular entity. So there is a small piece of Java program that is written for a thermostat. I'll show you that program. We'll look at the predicates in the program and see how to apply logic coverage criteria. In the next lecture for this week, I'll take you through another program, which is an elementary high school program, which basically takes inputs as three sides of a triangle and tells you what is the type of the triangle. Is it an equilateral triangle, isosceles triangle, and so on. It's a very good old program that not only in this book, in this lecture, you'll find it in several lectures in testing. So it's a nice thing, nostalgic thing to be able to go through that program once again. So what we'll do today is we'll begin with a thermostat program. So here is the code for the thermostat program that's taken from the textbook that we are following, the book on Introduction to Software Testing. I have taken the code as it is. The authors of the code are the authors of the book, as it's acknowledged here, right? So there is a class called thermostat. What do these lines 12 to 21 give you? They give you all the variables that this program handles, right? So there is an integer variable called current temp. Here, the right hand side, the comment tells you what it represents. It represents the reading of the current temperature. It could be the temperature of a particular room, right? And then the next variable is called threshold difference, abbreviated as threshold diff. It tells you what is the temperature difference until the heater gets switched on. And then the third integer variable says time since last run, which means what was the time since the heater stopped last time. So what is the thermostat trying to do? Maybe it's controlling a room in a building in a very cold region. It's trying to keep the room heated in a particular ambient temperature. So this program tells you when to switch it on, when to switch it off, and what will be the basic functionality of a thermostat. So the fourth variable is a Boolean variable called override. Override means the user switches off the automatic control in the thermostat and he is trying to configure the temperature setting himself. Then there is one more integer variable called overriding temperature, which means when the thermostat is in the overwritten mode, what's the temperature that it is being configured for. And there's another integer variable called runtime, which is when to run the heater on, when to turn the heater on and how long to run it. And then there is something called a period, which tells you whether it's morning, day, evening or night. Maybe it implicitly influences the temperature in which the thermostat will be running. And then there is another type, enumerated data type called day, which is of the type weekday or weekend day. So here is the main code corresponding to the thermostat. So the method that is called turn heater on, which takes programmed settings input as pset to the program. So there is a pre-programmed setting for the thermostat that is that is used to be able to turn the heater on. So here is the code corresponding to the thermostat. Please remember, in all these slides, when I show a piece of code, I show it across several slides so that it becomes visible. But you should, when you read it as a piece of code that is meant for continuous execution. And as I told you when we did graphs, it might be the case that the code as it is may not be taken and readily executable. It could be a fragment of a code. But we will focus on the things that we need in the code. So I may not give you the complete code, and the code will run through several slides. So here is the second slide where the code continues. This is the code corresponding to this method that begins in line 24. So what does this say? This method has another internal integer variable called dtemp, which basically tells you it asks you to input the setting, which is the period, which is the day, through this, right, pset. And then it has this code. So it says there's an if statement which has several conditions here. So it says if current temperature is less than D temperature minus threshold difference, or read this thing as or, override is true and current temperature is less than override temperature minus threshold difference, and time since last run is greater than minimum lag. So what it says is basically current temperature is, the room has become cold. Right, that's what the first one says. Second one says that the override is on, the Boolean variable override is on, which means the user is trying to take over and run the thermostat, and the temperature in the override mode is still minus the threshold. The current temperature is still less than that, so the room is again cold even in the override mode, and the heater has been off for some time. So what do I have to do? I have to turn on the heater. Right? When I say I have to turn on the heater, we also have to specify for how long to turn on, and assume that the heater heats at the rate of per degree Fahrenheit of heating, it takes 1 minute to heat. Right? So using this gradation in the temperature of increase in the temperature of heater, you specify how long to keep the heater on. If you keep it on for too long, maybe the room will become too hot. So you need to be able to set it so that the room temperature is just optimal and comfortable. So this is the code that does that. So it first computes the time needed to turn the heater on, which is the difference between the temperature in the room and the desired temperature dtemp. And then it says if override is on, then the time needed to turn the heater on is the difference between the current temperature and the overridden temperature. And then it says set runtime to be time needed, set heater on to be true, and then you return true. This is a method that returns a Boolean variable, right? Otherwise you say set heater on is false and you return false. So is it clear, please, what the simple code does? It's a code corresponding to a thermostat. It tries to keep the temperature in a room, in a building at an optimal setting. It uses all these variables which basically tell you what is the current temperature, for how long has the heater been on or off, and if whether the heater has been overridden in the override mode being taken by a user, in which case what do I do, and what sort of a day it is, morning, day, evening, night, or is it a weekday, weekend? Maybe weekdays all the people in the house, occupants in the house are away, so you don't have to turn the heater on. Maybe in weekends you have to keep it on for longer. All these things matter. Then it uses one Boolean method called turn heater on, which basically decides whether to turn the heater on or not. So that Boolean method has an internal variable dtemp, and then it has this if temperature, decides how long to turn the heater on, and does the settings and sets the turn heater on variable to be true. Otherwise it keeps the heater off and returns false. So now our goal is to be able to do this program, test this program by applying the logic coverage criteria that we have learned. So the first thing to look for when we apply logic coverage criteria is what are the predicates in the program and where are they. So you go back and look at the code in this program. The first part of the program just does declarations, no predicates here, obvious. Second part of the program has this long if statement here. There's one if statement which is this between lines 28, 29 and 30. And then there is one more if statement here at line 34, if override. So what I've done in the next slide is that I've told you what the two thermostat predicates are. So there is a predicate in lines 28 to 30. I just copied the predicate that occurs as the label of the if statement here. And there is one more predicate called override at line 34. So this is a pretty long thing, right? And maybe difficult to read. So let's simplify it. We call A as this. Current temperature is less than D temperature minus threshold difference. We call B as override. We call C as this clause. The current temperature is less than override temperature minus threshold difference. And we call D as time since last run greater than min lag. So there are four clauses: A, which is the first one, B, override, C, which is the third one, and D, which is the fourth one. Now the predicate looks readable in the notation that we are used to understanding it. What is the predicate basically? It is A or B and C and D. right? Where A is this first part, B is override, C is the third part, and D is the fourth part. And the next predicate override is just one clause predicate B. So this predicate, first predicate P, which occurs at lines 28 to 30, is interesting for us to test because it's got four clauses A, B, C, and D, and it's got a combination of ors and ands. So let's go ahead and test it for that predicate, right? So now if you look at this predicate has one internal variable called dtemp. We'll go back to the code for a minute. Remember here, dtemp is a internal variable that was local to the method turn heater on. The rest of the variables in these predicates are all inputs and outputs. So as I told you, we have to be able to do reachability first, which means we have to be able to solve and make sure that the predicate occurring in these lines is actually reached. Which means what? In this case, because it's a smaller program, it's easy to do. Solving here means just getting appropriate values for dtemp. Give a value for period and day for dtemp and let it get assigned to that value, and then you'll be able to reach this predicate. There are no other conditions. Clause A, as I told you, has an internal variable dtemp, so I have to be able to solve for dtemp. So I just give some values. So this is the line that is given in the program. And look at it. It says this P set is get setting period day. So I give it some value. I say period is morning, day is a weekday, and so that's it. I have assigned value to dtemp. Now what I do, I take back, and these are the four clauses A, B, C, and D. Please look at the title of this slide. It says I am testing for predicate coverage of this clause for the value of the predicate P being true. So what sort of a predicate is that? That's a predicate that looks like this. It's got two ands and an or. So one simple way of making the whole predicate true is to make all the four clauses true, which means I make A, B, C, and D, all of them true. That's what I've written here. I say A, which is current temperature less than desired temperature minus threshold difference, is true. B is true, C is true, and D is true. So to make all these things true, what should I give? I should give values for current temperature such that current temperature value is indeed less than desired temperature minus threshold difference. Override is a Boolean variable. I make it true directly. Similarly, to make C true, I should be able to make current temperature true and make the overridden temperature minus threshold difference to be a value greater than the current temperature, and so on. So here are a set of values that I give for the predicate being true, right? So I need this object thermostat, I need the object program settings, and then I pass value to dtemp by saying period is morning, day type is weekday, and then I set, let's say, current temperature to be 63, threshold difference to be 5, set some value. Is it clear that current temperature this A will become true, right? Because current temperature will be less than D temperature minus threshold difference. Why? Because this is 69, no? And then override has to be true. Now I'm working on clause C. I set overridden temperature to be 70, so that will again make C to be true because current temperature will be less than overridden temperature minus threshold difference. 63 is less than 65, and then to make clause D2, I set min lag and time since last run such that the difference is time since last run is greater than min lag. So time since last run is 12, min lag is 10, so it's greater than 10, so fine. Right? So if this slide, what does it contain? It contains the final set of test cases that will test which predicate, this predicate P occurring at lines 28 to 33 for predicate coverage being true. So similarly, for predicate coverage being false, I have to be able to give test cases that will make A, B, C, and D true or false appropriately. So for this predicate to be false, what could I do? I should make D false because it's an AND. Once I make D false, A, B, and C could be anything because anything ANDed with false becomes false, or I could make this whole thing false along with D being true or false. So like I did here, I decide what I want to do in terms of making each of the clauses true or false to make the predicate be false, and then I give values such that they're met. I haven't given them to you in my slides, but I hope it is clear how to do it. Now for the same predicate in lines 28 to 33, I want to be able to, let's say, attempt correlated active clause coverage, which was another coverage criteria that we saw. You could attempt any other coverage criteria. You could do clause coverage, you could do generalized active clause coverage, you could do inactive clause coverage. But I have put the CACC as an example to tell you how correlated active clause coverage is done for P. So if you remember the lecture from last week, to be able to do correlated active clause coverage, we have to take each clause to be a major clause and first make the major clause determine the predicate. Once the major clause determines the predicate, I write one set of test cases that make the predicate true when the major clause is true, and one set of test cases that make the predicate false when the major clause is false or true, right? So this predicate has 4 clauses, A, B, C and D. Each of these 4 clauses can take turns to be the major clause, and each of them can determine P. So I worked out for when A will determine P. If you remember from the last week's lecture, when A determines P will be called PA. So PA was obtainable by using this formula, right? So you make A true and XOR it with making A false in the same predicate. So I have reworked the solution for PA. So PA true is what? Substitute A to be true in this predicate. So you'll get 2 OR with B and C and D, XOR with false OR with B and C and D. Now you simplify this. True OR with B and C is nothing but true, so that will be true and D. False OR with B and C is nothing but B and C, so that will be B and C and D. I go on simplifying it further, then I get this final value. As I told you, in case you're not clear about how to go from these 4th line to 5th line and 5th line to 6th line, why are they equivalent? You could stop at 4th line or 5th line. They are equivalent, so in terms of obtaining PA, assuming that you had stopped at 4th line or 5th line, that's also good enough. You need not know how to simplify this to be able to get the last line. Even if it stopped here, it's good enough. So same way, we can determine PB, PC and PD. I have not worked it out for you, but in the same way you could do that. In fact, you must try and do it as a little exercise. So now what I have done is, here is how the test requirement for CACC will look like. So how do you read this? There are 4 clauses, A, B, C and D, and this PA is when A is the major clause, PB is when B is the major clause, PC is when C is the major clause, PD is when D is the major clause. When A is the major clause, these capital T and capital F in the column corresponding to A indicate that A is made true once, A is made false once. The rest of the values for B, C and D, indicated by small t and small f for true and false, tell you the values that the clauses B, C and D take for A to determine P. Similarly for PB, when B determines P, B is made true once, false once. The other clauses A, C and D, which are minor clauses, when B is the major clause, take values such that the predicate becomes true once and false once. Similarly for C, when C is the major clause, the true false values corresponding to C are written in capital letters. The rest of the clauses take values such that C determines P, and finally for D. Right? So now this is how I write and fill up the test cases. Now I examine this table once again to see how many repetitions are there in the table. So if you see row number 3, false, true, A is false, B is true, C is true, D is true, is the same as row number 5. A is false here, B is true, C is true, D is true. Please don't worry about capital T true being capital T here for B and capital T here for C. It just still means true. So these are basically duplicates. So I don't have to repeat. So if we ignore the duplicates, I basically need 6 test cases to be able to satisfy correlated active clause coverage criteria for P. What are the 6 test cases? The rows that don't come as duplicates, these, all other rows. So what I do, I take one row at a time, and like I did for predicate coverage, I give values to all the variables that makes each clause true or false in turn. Right? So for A to become true, here is the set of values. So A is this. For A to become true, current temperature could be 63, desired temperature could be 69, threshold difference could be 5. For A to become false, current temperature could be 66, desired temperature could be 69, and threshold difference will be 5. In this case, current temperature will not be less than desired temperature minus threshold difference. And D temp, we saw you have to pass that value by setting values for period and for D type. B is very simple because it's just this Boolean variable override. Similarly for C is this clause. I give values for current temperature, desired temperature, and threshold difference to make C true once, false once. Similarly for D. So once I have this, I go back to this table. For every row in the table, A true, B true, C false, D true, here is the test case. Read this as A true, B true, C false, D true in order A, B, C, D. Here is a test case. This is the complete test case for the first row in this test requirement for CACC. Similarly, I give 6 set of test cases, right? This is the second one. This is the third one. This is the fourth one where A is false, B is false, C is true, D is true. Similarly, this is the fifth one, all 4 are true. This is the sixth one, A, B and C are true and D is false. So these are the final test case values that will help us to test correlated active clause coverage criteria for the predicate P in lines 28 and 30. So similarly, you could do clause coverage for that predicate, generalized active coverage criteria for the predicate, RACC for the predicate, all other conditions that you want. Hopefully this exercise of this example would have helped you to understand how to apply logic coverage criteria for source code and how to write test cases end to end. What we'll do in the next lecture is I'll take you through another example slightly longer and more complicated than this so that you understand reachability and controllability well and tell you how to apply logical coverage criteria for that example. Thank you.